Today we're going to talk about the second derivative, which is just the derivative of the derivative. The notation we use, if we use the Lagrange notation, we just say f double prime. We put two hash marks instead of one, right? Two little prime symbols. So f double prime. We often just read that as f double prime. If we use the Leibniz notation, right, we're taking the derivative of the derivative, right? So d dx of dy dx. And as a shorthand notation then is just d squared y over dx squared. Okay, so it's a little odd, but it's just the derivative of the derivative, and it's a shorthand notation for d dx of dy dx. All right, so that's the notation we're going to use for the second derivative. Now let's back up a little bit and think about what the derivative tells us again. If the derivative of a function is positive, right? So remember that the derivative is the change in the function for a small change in the independent variable. Now this doesn't say what the independent variable is, but let's say it's x, right? If y equals f of x, right? Then this would be a small change in y. This would be the change in y for a small change in x, right? And so if the derivative is positive, that means that y is increasing for an increase in x, right? So we say that f is increasing on that interval. All right. Now, if the derivative is negative, less than 0, if it's negative, that means that for a small change in x, y is decreasing. Y is going down. It's negative, right? It's going in the negative direction. So we say that if f prime of x is negative, then f is decreasing on that interval. All right, now that's just a review. So let's look at a similar thing with f double prime. F double prime is the second derivative. So if the second derivative is positive on an interval, right? Remember that the second derivative is the derivative of the derivative. So that means that the derivative is increasing, right? Because the second derivative is the rate of change of the derivative now. And so for a small change in the independent variable, then f prime is increasing, all right, if f double prime is positive. And we've talked about concavity before, and so we said that if the rate of change is increasing, it's concave up, right? So if f double prime is positive, meaning that f prime is increasing, then it's concave up on that interval. So on the other hand, if the second derivative is negative on an interval, right, that means that the derivative is going down, right? If the derivative of the derivative is negative, that means the derivative is decreasing on that interval. And when the rate of change is decreasing, right, we said that the concavity is concave down. Okay, so remember, concave up looks like a U. Concave down looks like a upside down U. All right, it's just the curvature of a nonlinear function. So let's go ahead and take a look at example 1. So in example 1, we're just looking at the sign of the derivative and the second derivative, first derivative and the second derivative, and we just want to try to sketch the shape of the graphs of those functions. So I don't even have any axes or anything on this. But remember, let's see if I can get this whole thing on there, that when the derivative is positive, right, that means it's increasing. So f prime is positive, so this is increasing. It's an increasing function. If f prime is negative, it's decreasing. And if f prime is 0, that means it's neither increasing or decreasing. We could just say that it's flat at that point. It's horizontal. So that's how we would interpret the first derivative of a function, the rate of change of a function. If it's positive, it's increasing, negative, it's decreasing. And if it's zero, it's neither increasing nor decreasing. So it just is horizontal. All right, so let's look at the second derivative. If the second derivative is positive, remember we just said this. The second derivative has to do with concavity. All right. Second derivative tells us about the second derivative tells us about the concavity. So if it's positive, it's concave up, right? It looks like a U, like this. All right. If it's negative, it's concave down. It looks like an upside down U. And if it's if the second derivative is zero, well, then there's no concavity, right? It's linear, right? It's linear. All right, there's no, the first derivative is constant, right? So the second derivative is zero, right? There's no change. In the first derivative, if it's linear, sorry, yeah. So remember, for a linear function, the first derivative is constant, and so if you try to look at the second derivative of a constant first derivative, then the change in the first derivative is zero, right? For any change in the independent variable. All right, so let's take a look at what these look. Let's kind of sketch these combinations of first and second derivatives. All right, so in this first box, we want to sketch the curve for a case where the first derivative is positive, so it's increasing, and the second derivative is positive also, so it's concave up. So we're looking for a function that's increasing and concave up. Well, what I do is look at the u. Look at this u here, right? Part of the u is decreasing, and the other part is increasing. So this part is increasing, right? This part of the u is increasing. So that's essentially what it looks like. What an increasing and concave up curve looks like. It looks like the right half of the u, right? It looks something like that. Maybe not quite that vertical at the end. Maybe I'll do it like that. Okay, so that would be an increasing and concave up curve. All right. Now, if it's decreasing and concave up, that looks like the other half of the U, right? It looks like this. It looks like the other half of the U, right? Looks like the left half of the U. Now, I think I'm gonna wait a minute on this last one, because those are kind of some special cases. Let's just look at the concavity and let's look at the first and second derivatives here, when they're positive and negative first, before we tackle the zero case. All right, so if the first derivative is positive and the second derivative is negative, right, now we've got an increasing function that's concave down. So look at the u again and look at where is the u increasing, right? It's increasing on this half of the u, right? And it's decreasing on the other half of the u. So if a function is increasing and concave down, it looks more like this. Okay, so it has that sort of curvature. If it's decreasing and concave down, right, that's the case where f prime is less than 0 and f double prime is less than 0. So both the first and second derivatives are negative. That means it's decreasing and concave down, then it's the other half of the u, right? It's concave down and decreasing. So it's this other half of the u over here. All right. Now, if it's increasing and linear, right? If f prime is greater than 0, that means it's increasing. And f double prime is 0, that means it's linear. So increasing and linear just looks like that. And decreasing and linear looks like that. Okay, there's no curvature because the second derivative is 0. All right, now let's look at this bottom case first. Now, if both the first and second derivatives are 0, right, that means there's no curvature and it's not increasing or decreasing, so the function would look like that. Just look like a horizontal line. So this is horizontal. line. All right. Now these other two cases are a little bit different. Well, we have a case where f prime is equal to 0 and it's concave concave up, right? F double prime is greater than 0. All right, it's positive. Now there's not a curve, there's no function that would meet that, but you can have that case at a point. So let's say you have a concave up curve, right? And you look at the derivatives along this curve, right? Here on this part, this f prime is less than 0. Over here, if I look at the tangent line over here, its f prime is greater than 0 because it's increasing. But down here at this point where when it changes directions is a case where we can have the first derivative is 0, but it is that function at that point is concave up, right? So, oops, let me f prime, oops, hang on. Well, let me delete that. Hang on. Let me start that over. All right. F prime is equal to 0 at that point, even though the function is concave up. All right. So this can only happen at a point. So only at a point. Right? It's this point where a concave up curve is changing from increasing to decreasing. All right, so only at a point, this point right here. All right, so let's look at a concave down curve, right? So f double prime is negative, and it's the same situation. On one side of the curve, it's increasing, right? So over here, f prime is greater than 0. Over here, if I were to draw a tangent line, f prime is less than 0, right? The derivative is negative. The slope of a tangent line to the curve at that point would be less than 0. But up here, at this point here, where it's changing direction from increasing to decreasing, at that point, f prime is equal to 0. Okay? So again, this can only happen at one point, only at a point. Okay, and it's that point right there, right, where you happen to have a concave down curve, but at that particular point, the first derivative is 0. Okay, so these two cases can only happen at a point. All right, so that's probably enough for this example, and I will meet you in the next example.